All right, welcome back again, everybody. Today we're going to be doing, frankly, a relatively short section on triple integrals in cylindrical coordinates. So the cool thing is we get to learn a whole new coordinate system, and then we get to see how to integrate in that coordinate system. And the beautiful part is that it makes integration easier as long as your region can be described relatively easy using these new coordinates, cylindrical coordinates. Here we go. All right. So there isn't too much of an overview. We're just going to talk about the cylindrical coordinate system, and then we're going to talk about how to integrate in this new coordinate system. The other good news is that well, I'll say this to start. If you remember the construction of the mechanics of the Riemann integral that we've talked about several times now, this is going to sound pretty much the same, except slightly different, like in a new coordinate system. The other thing I will add is that the cylindrical coordinate system can feel a little bit weird at first, but hopefully I can make it simple enough that it doesn't feel so weird. All right, so let's talk about the coordinate system to get started. So in the cylindrical coordinate system, a point P in three-dimensional space is represented by an ordered triple r, theta, z, where r and theta are the polar coordinates of the projection of the point P onto the xy plane, and z is the directed distance from the xy plane to the point P. All right, so let me zoom in on this for just a moment. Here's our point P. We can describe the location of that point in three-dimensional space using these other coordinates that are not x, y, and z, right? Cartesian coordinates are rectangular. It's literally x, y, and z, right? But that's not the only way to effectively describe the position of a point in three-dimensional space. Another way to do it is to basically do a combination of polar coordinates and Cartesian coordinates. That's really what cylindrical coordinates are. You use polar coordinates for 2 dimensions, and then you use a Cartesian coordinate for the third dimension. So here, our x and y dimensions are given in terms of polar coordinates, and then our z dimension we just keep in terms of Cartesian coordinates. That's basically it. All right. Yeah, this is what I said just a moment ago. Cylindrical coordinates are just like a combo of polar coordinates and rectangular coordinates. Um, yeah, this is also what I just said. So in essence, cylindrical coordinates, they encode radial behavior in 2 dimensions and linear behavior in a third dimension. So you can kind of think about it like that. So we've seen examples of this before, but if your region is easily described radially in 2 dimensions and linearly in a third dimension, cylindrical coordinates can simplify things quite a lot. And we actually did see that in a couple examples already. I know we saw one in the example last section, and I'm pretty sure we saw another version of this. No, because we didn't really get to triple integrals until 15.6. So anyway, point is, cylindrical coordinates are handy when our region E is better described in this system. One good tip, like maybe a time you might want to consider cylindrical coordinates, is if you see this expression involved in your integral or in your function or your the description of your region, right? X squared plus y squared should kind of make you think polar, right? All right. So how do we convert between the two systems? What are the equations that relate the two systems? So to convert between these two systems, we use the isomorphism equations for polar coordinates, and then we just keep the third coordinate as it is. That's it. Okay, that's it. I guess the thing that you need to wrap your head around is that every single point in three-dimensional space can be described in this way. That's why they're called isomorphism equations. You could describe every point in three-dimensional space using Cartesian coordinates, or you could describe it using cylindrical coordinates. The representations are different, but the objects that we are describing have not changed, only the way we're describing them, right? And a nice thing about different coordinate systems, as we saw before when we were doing polar coordinates, is that they can express some fundamental objects in very concise and elegant ways. We're going to see that in this example right now. Right, so I definitely want you to try this one on your own. I want you to try to describe the surface, precisely describe the surface, whose equation in cylindrical coordinates is z equals r. All right? So think about this for a minute. Think what surface this could possibly describe if we're thinking in cylindrical coordinates. All right, now say something out loud. Remember, it doesn't have to be to anybody. It can be to yourself, or it could be to your dog, your cat, your hamster, anything. Just give your brain that audio feedback. Right. And now write something down. So now that you've said something out loud, try to write down precisely what what surface this is representing, and then we'll take a look together. Right, here we go. So just some details first. The first thing is that this equation is saying that the height at each point measured from the xy plane is the same as the distance r from the z-axis. So z is given by how far away you are from the z-axis at every height point, right? Theta also doesn't appear. So theta is everything. Theta is everything between 0 and 2 pi. Theta can vary, it's a free variable. Now, r is the radius of a circle in cylindrical coordinates, right? So if we wanted to look at traces of this surface, we could just set r to be different values, k. And then if you set r to be these different values of k, then what you're getting a circle of radius k centered at the point 0, 0, k. That's what's happening here. So if you can kind of think about how that looks, it's basically circle, 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 circle that gets wider as you go up and then smaller as you go to 0. And then the same thing going down. What object is that? It's a cone. It's a cone. That's what it is. So in cylindrical coordinates, this conical object, this cone, is super simple to describe. It's literally just z equals r. That's it. That's it. Cool stuff. That's what's nice about cylindrical coordinates. Now, let's do triple integrals in these coordinates. So we just saw that this can provide simpler representations of regions and objects, and this elegance combined with Fubini's theorem can help simplify our integration process in the right context. So again, you want to think of this new coordinate system as another type of tool that you can use to make your integration life easier. That's the goal, all right? However, if we want our integral to be able to scan these regions, we need to adapt our integral mechanics to this new system. And that's exactly what we're going to do right now. So now I hope I sound a lot like a broken record. I'm going to sound like a broken record again for the next two sections. But just as we did with triple integrals, if we're given a continuous function f defined on some bounded region E, contain E in what we're now going to call a polar rectangular box, a box R given by this. So quite literally, remember a polar rectangle from the polar coordinate section is kind of like looks like that. It's basically what you would get if you had a circular wedge, but then you chopped off the pointed part in a rounded way, right? So now extend this into 3 dimensions. And that's a polar rectangle. Oh, sorry, a polar rectangular box. So this is how we're going to define it. Again, we're going to define this function capital F using an indicator function that just says if you're on the set, you're going to have F, and if you're off the set, you're going to have 0. We're going to partition that polar rectangular box into polar subrectangular boxes by subdividing the respective intervals in each coordinate into L, M, and N subintervals of length R sub delta R sub I, delta theta sub j, and delta z sub k, respectively. So I hope this is getting boring now because it's like the same thing, right? Basically, partition your rectangle into a bunch of little sub-rectangles. And then we're going to choose a sample point. So this is kind of what the sub-rectangles look like. We're going to choose a sample point in each one. But here's the thing. If we want to effectively choose a sample point, x, y, z, we need to convert to a cylindrical representation using those isomorphism equations. So initially, our function was given in terms of Cartesian coordinates. And we could use these, but because we're talking about integrating in cylindrical coordinates, we need to convert everything to cylindrical representations. And that's what we're going to do. So remember that in cylindrical coordinates, x is r cosine theta, y is r sine theta, and z is z. The rest is a mess. So don't let the stars and the IJKs overwhelm you. Those are literally just indexing things to say where we're at. That's all. So quite literally like, oh, if we're at this particular box, then this would be the particular point. But r cosine theta, r sine theta, z. That's all that's happening here. All right, now if our function f is integrable, we can save ourselves a headache and we can choose all the subintervals to be uniform length respectively. So delta r, delta theta, delta z. Then the volume of each one of these polar subrectangular boxes is, remember, it's not just delta r, delta theta, delta z, but it's r times delta r, delta theta, delta z, right? That's how you get the proper volume. You can kind of see it here, even though this picture is using the differentials, right? R d theta, it's like r delta theta. That's kind of what's happening there. Then if we evaluate f at each one of these sample points, we can form this approximating Riemann sum. Remember, it'll be equal to little f because capital F is 0 when you are not on the region. And then this is what we get. So we're evaluating little f, in essence, at this point, and then multiplying by that volume right there, r delta theta, delta z, right? Now take the limit as delta v goes to 0, or equivalently as L, M, and N go to infinity, and then you get the following triple Riemann integral, like so. And r cosine theta, r sine theta, z, and there's that volume form right there, just like we've seen in the past. Except now there's another coordinate. That's it. There's a dz, right? There's a dz that's happening in this case. If the function f is continuous, then Fubini's theorem lets us integrate iteratively. We can swap the order of things, and we get this representation below. There we go. So nothing really has changed. The only thing that has changed is our coordinate system. And because we changed coordinate systems, we had to alter the representation of the points, and we had to alter the volume forms that we were using before. But everything else, intuitively speaking and procedurally speaking, is the same. So we're going to integrate between two surfaces first. Then we're going to integrate between two curves. And then we're going to integrate in between two numbers, assuming that our regions are nice enough to be able to do this, right? That's the whole thing. All right, that's pretty much the idea. Just want to point out again that this is really just equivalent to a change of variable in the integral from Cartesian to cylindrical coordinates. That's all it is. So remember, there's an extra factor of r, just like we saw before when we were doing polar coordinates. It's the same thing. It's the same thing. Exact same r for the exact same reason. That's all the same. The only thing that's really different is now we have another variable of integration, which is Cartesian in nature. So yeah, I said this last time too. In the next section, we're going to do this whole process again. We're going to reconstruct the integral again, and we're going to see a change of variable from Cartesian coordinates to spherical coordinates. And what you'll notice in that case is that we don't get r, we get a different factor. We get another factor that comes out. And then in the following sections, 15.9, we're going to totally generalize that procedure. And we're going to say, hey, what happens if you do a general transformation of the region? What comes out? Like, what does this extra factor really become? It's pretty amazing. I like it. All right, so let's try an example, okay? This is one I definitely want you to try on your own before we do it together in a moment. So a solid E lies within the cylinder, x squared plus y squared equals 1. Imagine it in your head. Below the plane, z equals 4, okay? Imagining. And above the paraboloid, z equals 1 minus x squared minus y squared. Okay, I can visualize that. Yeah, okay, I can see it. The density at any point in E is proportional to its distance from the axis of the cylinder. So, like, proportional this way. Find the mass of E. All right, so I want you to ponder this for a minute. Think about it, visualize it. Okay, now say something out loud to yourself, anything out loud to yourself about how you might proceed. All right, now try to work it out on your own. Remember, we're given a density function representation. The density is proportional to the distance from the axis of the cylinder. Keep that in mind. So come up with your density function and try to describe your region. And you're going to notice that it's easier to do in cylindrical coordinates. All right, here we go. So I'm going to draw a quick sketch because I know I don't have a sketch on here, but when I try to visualize this, I can see the cylinder. The cylinder is easy to see, right? Oops. Hopefully that's not too bad for you to visualize. I should have made a better cylinder. There we go. Make this a little bit nicer, like that. Okay, and we're below the plane z equals 4. So maybe what I need to do is do this, maybe this and that, x, y, z. We'll say this is when z equals 4, so we're chopping off the cylinder at 4. And then we are above the paraboloid, z equals 1 minus x squared minus y squared. Above the paraboloid. So this thing right here is z equals 1 minus x squared plus y squared. So it's a paraboloid that's like opening down. So it kind of looks like this. There we go. It's like opening down, and it's got a vertex right at 1. So the vertex right here is when z is equal to 1. Yeah, it's equal to 1. Okay, and so what the region E looks like is everything in between this plane up here and above this paraboloid right there. So really what we're looking at is this region kind of in here, but you know, it's 3D and I can't twist it around on this page, but that's what it looks like. So that's the region we're integrating over. And what does our density look like? Well, our density is proportional to the distance from the axis of the cylinder. Axis of the cylinder is the z-axis. So the distance is going to be x squared plus y squared. Take the square root. Yeah. All right, what do I have here? So, yes. Yes, okay. So here everything is given in Cartesian coordinates. Now we're going to convert things into cylindrical coordinates. Remember, in cylindrical coordinates, cylinders are easy. Cylinders are just given by r equals 1. That's all we need. Theta is a free variable, z is a free variable, so the cylinder that I had sketched, actually I should just say this one, that is this right here. The paraboloid is given by z equals 1 minus r squared. That also makes sense, right? Because x squared plus y squared is r squared. So that's what we're getting there. So the way that we can describe our region is this. Theta is anything. Theta goes between 0 and 2 pi. R goes between 0 and 1, right? So you're only going to go out 1 unit. And then z is going to go from the top of that paraboloid up to the plane z equals 4. So this is the cylindrical representation of our region. Now, since the density is proportional to the distance from the z-axis, this is our density function, some constant of proportionality k times the distance from the z-axis. Written in cylindrical coordinates, we just get kr. So it's nice when things are proportional to distances, right? Which is fairly common. All right, now we have the region, we have the density function. Another thing I will point out is that this density function is continuous. It's continuous on all of R3. So that means that we can iterate our integration process by Fubini's theorem. And here's what we get. Oh wait, yeah, here's what we get. We're just looking for the mass. So we're adding up all the density times the volume. So here we go. Density function, right now it's a triple integral in terms of Cartesian coordinates, convert everything to cylindrical and iterate, this is what we get. So we're doing r dz dr d theta in this case, because that's the easiest way to integrate. Remember, you can change the order of integration if you want, you just have to be careful how you do it. All right, so do this. Yes, r, there's our volume form, there's kr. Z goes between these two surfaces, r goes between these two numbers, theta goes between these two numbers, and here we go. Integrate with respect to z first. That's super nice because this doesn't depend on z. So we get that. Now we can split it into two separate integrals. We can do a product of two integrals because the remaining function uh, doesn't depend on theta. So we get two separate integrals. Apply FTC2 twice. You get this, simplify, and you get that. So that is the mass of that region. 12 pi k for whatever that constant is, divided by 5. All right. And that's it. That's it. So on that note, let's play. I hope you enjoyed this lecture. I know it's relatively short. The next one is a little bit longer, I think, but I think at this point, if you kind of understand the mechanics of the integral, everything's good, right? All right, I will stop rambling. I'll let you off a little bit early this time, and I'll see you next time.